Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at derivatives of exponentials and trying to understand how they work. Let's begin by defining what an exponential function is. So definition, a function of the form, a function of the form f of x equals a to the x, or sometimes just written y equals a to the x, where a is non-zero, so a has to be positive, is an exponential function. So obviously examples of exponential functions are plenty. So we've got something like, say, f of x equals 2 to the x, that's an exponential function. Y equals, say, 5 to the x, that's an exponential function. G to the x equals 1.29 to the x, that's an exponential function. Indeed, we can even have sort of irrational numbers as taking a value for a. So an example would be, say, h of x actually being pi to the x would actually be an exponential function. I should make a remark here, and the remark is a actually cannot be less than 0 in our above definition. And why is that? Because let's take an example of a actually being minus 2, right? So if a is minus 2, then the exponential function would be y equals, say, minus 2 to the power x, okay? But because x can be any real number, because basically we have a function where x is our input and y is our output, then our inputs, we can sort of take any real numbers, but then we're going to start to run into problems, because if I take x equals a half, for example, then minus 2 to the power of a half is actually taking the square root of negative 2, which is not defined in the case of reals, right? Let's have a think about the behavior of exponential functions. Obviously, a good way of being able to understand the behavior of functions is to be able to graph them, because then you can see exactly how they're behaving with a picture as opposed to with sort of symbols and formulas. So let's consider three cases. So let's consider case 1, where a is actually bigger than 1, and then case 2, where a is actually equal to 1, and case 3, where a is actually bigger than 0 and less than 1. So perhaps I can tidy that up a little bit. Good. So a is bigger than, obviously the functions we're considering, I should say, is f of x equals a to the x, right? Where x can be any real number as an input. So you can obviously go away and sort of do a table. You can have your x values, you can have your f of x values, and you can create a table, and then you can sort of start to put in, say, okay, it's going to be, say, 0.1, and then I'm going to maybe get 1 and then 2, and I can then fill in what the values here are going to be, right? I won't sort of go into those sort of details. I'll just give you an overview of what the graph's going to look like. You can put the numbers in and sort of check for yourself that what I'm saying is sensible. So the graph of a to the x for a being bigger than 1 is actually going to be a function which is just going to be going up and up and up and up and up, right? And if you just want to have a think about why this might be the case, just think to yourself, what's going to happen if you consider 2 to the power x? As x gets bigger, 2 to the power x gets even bigger. So it's unsurprising that the graph is just going to be sort of going upwards, right? What is interesting is the point on the y-axis actually is actually going to be y equals 1. And again, we can check that when x is 0, f of 0 is going to be a of 0, which is actually just going to be 1. The other thing of real interest is actually what's happening on the x-axis, in particular for the negative part of the x-axis. So let's have a think about that. Well, imagine if x is less than 0, so x is negative. So let's take x to be equals to negative n, where n is positive. So since n is positive, the negative n is negative, right? Then our f of x in this case would actually become f of negative n would actually become a to the negative n, which is 1 over a to the n, right? And since our n is positive, we've said, because that's the condition we're using to make x negative, then what we can basically look at and just see what happens. Well, if n gets bigger, so as n gets sort of larger, x, which is negative n, actually goes to negative infinity. But then as that happens, a to the n, right, actually goes to infinity. But if a to the n goes to infinity, then 1 over a to the n better go to 0, which means the curve, I should perhaps mark it explicitly, that section of the curve is the y values are going to get closer and closer to 0, which means the graph is actually going to taper off and get closer and closer and closer to the x-axis, right? It is indeed going to form what's technically called an asymptote, which means it's going to get arbitrarily close to the x-axis but never actually touch it. So in a nutshell, that's basically going to be the graph of a to the x for a being bigger than 1. Let's consider case 2. So in this case, we're going to have a equals 1. So f of x is actually going to be a to the x. It's just going to be 1 to the x. But 1 to any power is just 1. So the graph is actually very, very obvious. The graph is just a horizontal line in this case. Of course, the y value is still 1. Now let's think about case 3. Case 3 is actually, I could go through all the details as I've done for case 1, but I think for the purposes of time, I'll spare you the details. Perhaps you could spend a bit of time thinking about this yourself, but basically we're going to get the same sort of behavior as we got in case 1, but now the roles of the positive and the negative have actually been reversed. So what was happening with positive x values in the case 1 case will now happen with negative x values in the case 3 case, and vice versa. So it is still going to go through the y value at 1, but everything else is gonna be the same. And of course, the important thing to stress here is there is an asymptote here, right? And it's going to be asymptoting to the x-axis. So perhaps I should mark that here and then do the dotted line to say there's an asymptote. So the asymptote, I should have said that earlier actually, the asymptote is to the x-axis. And that's the key thing. So the asymptote here is also to the x-axis. So moving on to actually calculating the derivative of exponential functions, we obviously so if we go back to sort of part 1 of this video series on differentiation, we used the definition of differentiation in terms of limits to be able to calculate some derivatives. And in that case, we showed that for exponential, sorry, not exponential, for polynomial functions, if we have something of the form x to the n, we could actually differentiate it using the definition of the limit to get nx to the n minus 1. So we're using the limit definition of a derivative to be able to get nx to the n minus 1. And then from that point onwards, we just referred to the statement in the red and sort of used that directly rather than going back to the limit definition. But in this case, since we're starting looking at derivatives of exponentials from scratch, we've got to go back to that limit definition. So let's go back to the limit definition. So say let f of x equals ax, right, where a is bigger than 0. Perhaps I'll get rid of this thing in red here because it's just giving me 2 definitions for f, and that's not a sensible thing to do in mathematics. So the derivative, if I go back to my exponential function, is going to obviously be the limit as h tends to 0 of f of x plus h, and then you take away f of x from it, and you divide the whole thing by h. So let's write that down. So I'm going to have x plus h as a power because I'm evaluating f at x plus h, and then I'm going to have a to the x, and the whole thing is basically going to be over h. And now here, perhaps we can write down the numerator by using rules of indices to be able to expand out the powers in some way. So a to the x and then a to the h, and then minus a to the x, and the whole thing is actually over h. And at this stage we can factorize this, right? Because I've got sort of common terms. I've got a common term there and a common term there. So I go back and say, well, I can take a to the x out, and I'll just have a to the h minus 1, and the whole thing is going to be over h. So since the limit is actually with respect to h, and the first term here of our factorization actually has nothing to do with h, that plays no part in the limit. So we can just take that out and have the limit just be applying to everything else, right? So we get an expression like this. And now this is where we basically get a little bit stuck, because we have to now go away and figure out what this limit is actually going to evaluate to give us. Now, it shouldn't come as a surprise since we've kept a sort of general. We've said it's some fixed number, but I've not told you exactly what that number is. I've just told you it's something that's not going to be negative or zero. What's going to happen is every time you go back and choose a different a, and you start to put different h values into this expression in the box, and you make h smaller and smaller, you're going to get a different value for the limit, right? So generally, as a way of trying to get the derivative, even though technically this is the right thing to do and the argument would go through, this isn't the most fruitful. This isn't the most fruitful, particularly from the point of view of the A-level syllabus and being able to understand these things. This is rather sort of dry and technical. So let's have another approach at this. Let's have another way of thinking about this, which is going to be more of a graphical view on how we can get sort of a derivative of a curve in the case one that I sort of drew earlier. Since we're resorting to a graphical approach, a good place to start would be with an actual graph of our function. So let's quickly write our exponential function down. And because I'm going to consider case 1, let me just say a is bigger than 1. But actually, similar sort of analysis would give us the results we're gonna arrive at if you were to take a to be between 0 and 1, or a equals 1, say. Right, so we've got x and y, and we know that our graph is going to look something like that. Good. So once we've now got this, how can we actually get a derivative? We can get a derivative by going to each point, or say not even necessarily each point on the curve, lots of different points on the curve, and quite frankly drawing tangents to them, right? Drawing tangents to them. So let me try and draw the tangents in sort of different colors. So here's a green tangent, and then the next one I'll draw maybe might be a blue tangent, and then the one after might be a green one again, and then the one after might actually be a blue one again, and so on and so forth, right? So we can start to draw tangents and then measure the gradients of those tangents by hand by measuring the change in y and the change in x. And once we've got that, we can start to get a picture of what's happening to the gradients and maybe describe that as a function, right? That can easily work. It takes a bit more effort, but that can certainly work. However, uh, let's try and be a bit more sort of analytic in this rather than having to do all these calculations. And the more analytic way of thinking about this is the first thing to notice is, well, look at the graph of this exponential function. And indeed, all exponential functions where a is bigger than 1, the graph is going to be sloping up, as we know, which means the function is an increasing function, right? So f of x is an increasing function. And this is obviously further reinforced by the fact that all our tangent lines in blue and green are actually sloping upwards. So we know this is an increasing function. Well, another way of saying that is basically saying that is that the derivative of f is actually going to be positive. That follows directly from the definition of what an increasing function is, right? Perhaps I can say another word on that, right? So if I've another way of saying what an increasing function is if x2 is bigger than x1, where say x1 is here and x2 is here, the 2 points on the x-axis, then a function f is increasing if the f of x2 is bigger than the f of x1, which means if you basically go up and then you go to the y value here, and then you go up and you go to the y value here, if you call this y value y1 and the other y value y2, which obviously is f of x1 and this is f of x2, then the second y value is going to be bigger than the first y value. This is just another way of saying that this is an increasing function, right? But now let's link this definition or this understanding to this condition here. And how we're going to make that link? Well, we're going to make that link by saying, well, let x1 just be called uh, x and x2 actually be called x plus h. And h has to be bigger than 0 because x2 is bigger than x1, right? So now our condition here actually becomes f of x plus h is bigger than f of x. But from that condition, I can basically say f of x plus h is actually bigger than f of x, right? In this way. So basically, when I subtract the big one from the small one, I'm still going to get something positive. But we know that h already is positive. That's the way we've sort of defined what x2 is by saying take h to be positive. Then that tells me that this thing here over h has to be positive because the numerator is positive and both the denominator is positive, which is basically another way of just writing a derivative down without taking the limit, right? So we know that an increasing function would satisfy this sort of condition. So I didn't actually describe this way of thinking about an increasing function in the video part 3 of this series, I believe may actually be part 4, uh, where we looked at increasing and decreasing functions, was because perhaps I thought at that time it was a bit too heavy, but now that we've seen all that material, hopefully this would reinforce some of those ideas and give you a slightly better understanding of what's happening. So good. So the key idea to take away from this so far, as I say, is the function is increasing. Now, the second thing that I would like to really emphasize is if I make A bigger. So imagine that this graph I've got in black is actually for, say, A equals 2. So let me write that down, A equals 2, say, right? What would happen if I wanted a graph for A equals 3? Well, if I wanted a graph for A equals 3, you can go away and sort of have a think about this. Uh, what's actually going to happen is the graph is going to be steeper on the positive x part and it's going to be less steep on the negative x part. It's still going to have the same behavior. It's going to pass through that red point, which is y equals 1, x equals 0, y equals 1. But the graph is going to look like this. So what does that actually mean? Let's make a bit of room and then sort of continue thinking about this. This is slightly better. Let's redraw those graphs slightly quickly. So I'm going to just quickly draw one of the graphs was like that, and then there was another one in pink which was like this, right? And there was a common point where they were meeting, which was on the y-axis at y equals 1. So we know that both graphs are of form f of x equals a to the x, and both are increasing. Both are increasing functions. But are they both increasing by exactly the same amount? They're not. And how do we know they're not? Because if I basically take some x value, say an x value here, right? And if I go up to the two y values, one on each curve, and then I consider the tangents, right? So that's tangent for the first one, and let me do tangent to the second one in a slightly different color so this sort of stand out, right? And we see that the tangent line to the graph in pink is steeper, right? So so the key point to take away from here is they're not both increasing at the same speed. What we can say is for larger values of a, the function f of x equals a to the x is is increasing at a faster rate, right? So there's one more observation we need to make, and then following that, we'd be able to write down the derivative, or at least sort of write down something sensible about the derivative in the case of these sort of exponential functions. So putting the two observations that we've actually made so far, the first observation was that the derivative is actually positive, and the second observation is just above, right? Which I'll sort of label maybe 2 here. So putting 1 and 2 together, what we can actually say that there has to be a very special graph. There has to be a graph which obviously looks give or take the same as the ones we've actually seen so far because they're all going to be of the form uh, ax, right? But what's special about this graph is as you go to each point on that graph, the gradient of the tangent at that point is just going to be the same as the y value. And you go to another point, then the gradient of that tangent is actually just going to be the same as the y value, which is obviously the height, right? And the same thing is going to be true for every point on that graph. Well, how do we know this? Because we know that uh, the functions are all going to be increasing, which means the gradient's always going to be positive, and we also know that the y value is always going to be positive, right? So and we know that they're actually changing. So as you change a, both the speed at which the function is sort of curving up is changing, and the y values of the function are changing. So because that's a continuous process in a way, there has to be a case in between where, as the graph starts to curve up, the tangent lines are going to be exactly as steep enough as the actual distance between the x-axis and the y-coordinate of each point, right? So for that special case, what do we know? Well, we know that the tangent lines are going to have equations of the form y equals mx plus c, where this m is going to give us the gradient of those tangent lines, right? And we also know that dy by dx is actually going to give us the gradient of our curve y equals a to the x, but obviously we don't know the exact expression for dy by dx. But as I say to you, in this special case, so I should say special case, in this special case, we actually do know what it's going to be. It's actually going to be the gradient of these tangent lines, and we want the gradient of these tangent lines to be the same as the y values. So here we go. We've managed to arrive at actually a condition. We've managed to arrive at a condition which some very special exponential functions actually satisfy. So we can now use this condition to start to say a little bit more. To continue with our trail of thought, so we know that there's a special A. I'm going to call it A special, very unimaginatively, such that when I have the function A special to the power x, it's got to satisfy this condition. It's got to satisfy dy by dx is equal to y, right? I'm going to put that in a bubble. So in this case, I know what my y is. My y is precisely A special. So hey presto, we've managed to work out our derivative, right? Now the natural question to ask is, well, what is this value of A special? We know that A has to be bigger than 1, and that tells us that A special has to be bigger than 1 in value, right? But what is it exactly? This will take a bit more sort of thinking, um, and we need not necessarily get into the details here. I think we've done a lot of detail already for the purposes of the A-level syllabus. So I will just tell you this A special value actually has a very special name, and it's called the number E. In terms of a numerical value, E is approximately 2.7182, and then it sort of carries on because E is actually an irrational number, right? So what we've actually been able to show, just to summarize this, if y is equal to e to the x, then dy by dx is actually e to the x. And this is a remarkable statement. We can actually think much sort of harder and longer about more functions of the form sort of a to the x. Uh, Again, I think for our purposes now we've sort of seen sufficient detail, so I will just write down what we need to know, which is if you actually go away and do the same sort of analysis that we've done with different values of a, you can sort of figure out that you can actually write every a to the x as something in the form e to the kx, right? This is like saying if I've got 10 to the power x, I can write that as something 2 to some power k and then to some power x, right? Which means basically I'm going to choose a k to make a power of 2, which will give me 10, and then I'm going to raise that to the power x. So since we can do that, rather than differentiating a to the x by itself every time, like the way we've done, we go back to using e because e happens to be very useful. And the same sort of analysis that I've done above actually goes to show that when you differentiate e to the x, you actually just get ke to the kx. So I'm now going to put these two results in actual boxes because they are the entire purpose of this video. So now we'll spend a little bit of time maybe doing a few examples. Let's look at the first example for this video. So we've got lots of exponential functions we want to differentiate, and of course because they're exponential functions we're going to be using the same sort of result that we actually saw on the previous slide or previous screen, which is going to be, so when I differentiate e to the kx, I'm just going to get ke to the power kx, where k can actually be any real number, right? So using that alone, I can just differentiate the first function. So when I differentiate 5 times by e to the x, well, okay, so the e to the x is going to differentiate to give me e to the x, and now we've got to go back to one of our rules of sort of differentiating functions in general. We know that if we've got a function of the form, let me not use a, let me use alpha f of x, where we've got capital F is equal to alpha f of lowercase f, then if I differentiate the capital function, I leave the alpha alone and I differentiate the lowercase function. We actually showed this being true for all sort of functions that are differentiable, so we can just use that to be able to say, well, the 5 in this case is just going to come along for the ride, right? So part 2 of this example, again, I'm going to use the statement in red and the statement in purple together. The 2 is just going to stay where it is, and then using the statement in red, the e to the 3x is going to give me 3 at the front, and I'm going to have e to the 3x as the thing in itself. So I'm going to get 6e to the 3x. So that's the second function differentiated. Let's now think about the third function. So here I'm again going to have to go back to something that we've already seen, which is if we've got two functions that are actually being added up. So if I've got an f and a g, lowercase, combining to give me an uppercase f, then I can differentiate the uppercase f by just differentiating each of the two functions on the right hand side and adding up the result, right? So I'm going to use that together with actually the statement in purple and in red to be able to write down the derivative for g. So when I differentiate my g, I'm going to get 3e to the 3x and 5 times by 2/5 e to the 2/5 x. And of course this can be tidied up because the fives are going to cancel, of course. Let me perhaps use a different color to do this in. So the fives are going to cancel. So the result is just going to be 3e to the 3x plus 2e to the 2/5 x. Lastly, let's look at part four of this example. In this case, the function we've written down, I've deliberately expressed z as a function of t just to sort of make things a bit more interesting, symbolically speaking. But really, there is no difference in terms of the mathematics here. We're just using different symbols to sort of do the exact same job as what we would use x and y for. So in this case, the derivative is going to be of z with respect to t. So that's what I write down. And then I differentiate each term by itself, right? So let's differentiate the first term here. So 6 times e to the 2t differentiates to give me 12 e to the 2t. And then the second term, well, we've already differentiated this above. So if we've got 5e to the t, that's exactly the same thing as what we differentiated above, whereas we called the independent variable x and not t. So I'm just going to get the same result as I got earlier. So it's just going to be 5e to the t. And finally, a constant function. Well, that's just a polynomial, and we know constant function differentiate to give us 0. So in fact, I need not even write it down. So we've now been able to work out derivatives of some sort of exponential functions. In the next example, we will look at more derivatives of slightly more complicated exponential functions. So let's look at more derivatives of exponential functions. Again, in this case, we're going to be using pretty much the exact same ideas that we've sort of used so far. Because of sort of lack of space on the screen, I won't write all the things down. I'll just sort of work through directly. But if you are unsure, do just feel free to go back, look at example one, make some notes, and then come back and then try some of these questions. So the first one, I do need to get this in the form e to the sort of kx by itself. So the only way to do that really is to be able to expand this, right? I wouldn't be able to differentiate this the way it is as it is currently. So when I expand this, I'm going to get e to the x times by e to the 4x, and we're going to add the power. So I'm going to get e to the 5x for the first term, and then I'm going to get minus 2e to the x for the second term. So once we've now got the terms in our standard sort of form, we can differentiate this quite directly. So f prime x is actually going to give me 5e to the 5x, and the second term, the minus 2, is just going to stay there, and e to the x differentiates to give me e to the x. So we've been able to do the first example. The second one, again, we don't know how to differentiate fractions yet, right? We found the same problem with sort of standard polynomial things that we were differentiating earlier. So in this case, again, what we've got to do is express this in the form e to the kx, right? And how can we do that? Well, again, just using rules of indices. So I'm going to say 27x minus 6x, which is going to give me 20x. So once I've now got this, I can differentiate this directly. Let's make a bit of room. So I differentiate this directly to say, well, okay, the 5 is going to be there for the ride, and I'm going to have 20e to the 20x by the sort of standard formula that we've seen already uh, earlier in the video. So part 3 of this example, exactly the same reasoning as the parts 1 and 2, which is I've got to get this in the form where I can basically go back, and I will write the formula down this time because I've sort of referenced it so many times, it's almost necessary to at least just write it down so it's absolutely crystal clear. So yeah, so I'm going to use the formula in red, where of course k can be any real number, of course, right? So to be able to get the expression in my form like this, I will just apply that power to everything in the bracket, right? So I'm going to get 2 cubed, and then I'm going to get e to the 5x cubed. Just figuring out what the first term is going to be. 2 cubed is 8, and e to the 5x cubed by, again, rules of indices, is going to give me e to the 15x. So let's make a bit of room so I can differentiate my newfound function in a nice form. So I differentiate this because it's described in terms of g. The derivative is going to be in terms of g prime. So it's going to be 8 times by 15 e to the 15x. But of course, 8 times by 15 is nothing other than 120, right? So it's 120 e to the 15x. That's the answer. Of course, I should go back and say for part 2, I should have said it's 100 e to the 20x. So now part 4. Again, this is just exactly the same as all the other things we've done. It's just that now the symbols are called u and s as opposed to x and y. Or y and x rather, but the functions are very much like the ones we've already seen, so I've just got to expand this to get each term here, and I've got to somehow find a way of being able to break this fraction into two separate parts whereby I can differentiate each part. So let's write this down. This is of course going to give me 4e to the s minus e to the s times e to the s is e to the 2s because you add the powers. And then coming to this fraction here, let me mark this out. So I'm going to separate this into two. That's going to be one of them. And then the other one is going to be this fraction here. So e to the 2s divided by e to the s is just actually going to give me e to the s because 2s minus s is just s. And then there's a minus there, and e to the 3s divided by e to the s is just going to give me e to the 2s, right? So now at this stage, it is worth actually combining some of these terms. So you see I've got an e to the 2s term there, and I've got an e to the 2s term there, and I've actually also got, if I look at this more carefully, I've actually also got an e to the s term there and an e to the s term there. So let's put all of this together. So the blue terms are going to combine to give me 5e to the s, and the green terms are going to combine to give me minus 2e to the 2s. So now we can just differentiate this directly, right? I'll write it here. So we get du ds, and what's that going to give me? Again, the exact same formula that I wrote down in red earlier would actually do the job. It's going to give me 5e to the s. The 5 comes along for the ride, the e to the s differentiates to give me itself, right? And then the second one, the minus 2 comes along for the ride, and then e to the 2s gives me 2e to the 2s, but of course I can simplify this because 2 times 2 is minus 4, or 2 times minus 2 rather is actually minus 4. So we've been able to work out our derivative for that last part too. Let's move on to example 3. In this case, we have to work out a tangent line and a normal line to our function or curve y equals e to the x at the point 0, 1. So this is a fairly standard sort of thing with regards to application of differentiation. So let's have a go at this. So we know that y equals e to the x is our curve, right? Is our curve, and we want to work out sort of equation of tangent, say first. Equation of tangent. Well, how are we going to do this? Well, we know that it's at the tangent's a straight line, so it's going to have equation mx plus c, where m is the gradient of tangent, and c is the y-intercept. Well, how am I going to get my gradient of tangent? I'm going to get my gradient of tangent using differentiation because differentiation actually gives us gradients, as we know. So I'm going to differentiate this y this time. I've got to be very careful as to what y I'm differentiating. So it's the curve. But we know that the exponential function is very special. It's the only function that differentiates to give itself. So we're going to write e to the x down. But the point we're working with, we don't just want a generic gradient as a function. We want the gradient at a point. So the point that we're actually working with is actually x equals 0, y equals 1. So I'm going to substitute x equals 0 into here. So it's going to be e to the 0, and that's actually going to give me 1. So that tells me my gradient, actually, so m equals 1. We've just been able to figure that out, right? Now, the other point to keep in mind is since tangent passes through point 0, 1, then actually my c is actually also 1 because the point is so special, it already tells me what my y-intercept is going to be. So I need not go to sort of my equation of line and then substitute in x, y, and m to be able to work out c. I already know what the value of c is going to be. So since we actually have a value for m and a value for c, which quite nicely there, we can actually write down the equation of the tangent, which is going to be y equals 1x, because m is 1, plus 1, because c is 1, right? So we've been able to work out the equation of our tangent to the curve at our point. So I'm just going to put that in a box, perhaps in a different color, just so it's absolutely clear. So now we can move on to looking at working out the equation of the normal. Let's have a go. We're working out the equation of the normal. Now, if what I'm about to say sounds unfamiliar, then please go back and take a look at part 4 of our video series on differentiation. We've covered an example of calculating normals in quite a bit of detail there. So that should help you. Otherwise, I hope this is useful. So the idea we actually need to use, we've got to use this fact. And what is the fact? The fact is that the gradient of tangent at a point to the curve times by the gradient of normal, perhaps I can write with a lowercase n, of normal at that point to the same curve, multiply to give you minus 1. A common way in which that's written is m1 times by m2 is equal to minus 1, where m1 is the gradient of the tangent and m2 is the gradient of the normal. So we need to find the gradient of the normal. The way we're going to do this is actually figure out the gradient of the tangent and then use that. But we already know what the gradient of the tangent is because we worked that out just before. We know that the gradient of the tangent, because the equation of tangent is this, y equals x plus 1, is equation of tangent. Then that tells us that m1, which is the gradient of tangent, is actually just 1, but then that tells me that m2 is actually minus 1 over m1, which is minus 1 over 1, which of course is minus 1. So we've actually figured out the gradient of the normal, but now we know that point 0, 1 is where the line, I should say the normal line, passes through. But this is a very special point, just like in the case of the example that we did about tangents. The reason why this is special is because this is already on the y-axis, right? So this basically tells me that because my equation of normal is going to, again, it's a line, it's going to have form y equals mx plus c, but obviously the m in this case means the gradient of the normal, and the c in this case means the y-intercept of the normal. So to go back to what I was saying before, which is the point 0, 1 tells me that actually c equals 1 in this case, right? So the y-intercept is 1. So since I actually have the gradient as being minus 1 and the y-intercept as being 1, I know that the equation I'm actually after is going to be minus 1 x plus 1. So we've also been able to work out the equation of the normal. Now, I will just mention a quick remark here, which is it's good to see that actually, if I just was to draw a quick graph, that my curve is going to look like that. This is my e to the x graph, and obviously my x and y axes. And the point we picked was this special point here, right? The point 0, 1. So it's the point on the y-axis at sort of y value 1. The tangent actually worked out to be this equation here, which was y equals x but shifted up by 1, and the normal actually worked out to be this equation here, which was y equals minus x but also shifted up by 1. And the point of interest here is obviously the fact that these two lines we know for a fact are going to meet at 90 degrees because y equals x goes at 45 degrees to the x and y axes, and y equals minus x also goes at 45 degrees, but from the other side, so that from the second quadrant of the x and y axes. So we know the angle between the y equals x line and y equals minus x line is actually 90 degrees. Uh, so I hope you found this useful. To end this video, I would just like to make some sort of disparate comments. What I did want to say, so the first thing I wanted to say was we should have noticed that exponential functions, either y equals e to the x or actually y equals a to the x for a being bigger than 0, do not have a stationary point. Do not have a stationary point, right? So there is no place on the, so let me actually draw a quick sketch. So if I actually draw this graph of y equals a to the x, perhaps this is a better way of explaining it. we know that the derivative of these sort of things is somehow going to be related to this sort of an expression because we actually showed this. I shouldn't even say expression, I should say equation. It's going to be related to this sort of an equation, but because the y is never actually going to be zero, because if you take a look, the curve is asymptotic to the x-axis, right? So the only time y is going to be equal to 0 is if the curve actually hits the x-axis, but the curve never hits the x-axis. So y is never going to be 0, and because this condition in the green box is supreme, that means actually dy by dx is never 0 for standard exponential functions, since y is never 0, right? So that's one point I actually wanted to make. The second point I wanted to make was I had the entire discussion for working out the equation in that green box by basically taking a to be bigger than 1. So we considered the case where all the graphs were actually like this, essentially, right? Of course, we could have gone back and looked at the case where a was actually not bigger than 1, but a was, say, bigger than 0 and less than 1. And in that case, all our graphs would actually look like this. Needless to say, or as I've already said before, I should say, the 2 points in red are actually going to be the same. They're both going to be the point 0, sort of 0, 1, right, on both these graphs. But the graphs would look somewhat different, but all the arguments we made would still actually go through. And again, it's reassuring to see in this case, in the case of a being between 0 and 1, you can again see uh, the graph never touches the x-axis, so the asymptote is still there, and the first point I made about there being no stationary point still actually holds true. So having said that, I just wanted to make a third point with regards to, well, what are these exponential functions actually good for? Well, they are very, very, very useful in all sorts of things, from physics to sort of engineering. One thing exponential functions are actually good for is study of populations, right? Because you can sort of see that if you consider a graph of time and population, and if conditions are good and the population is going up, you're going to get something like this. You're never going to have a case where, say, well, hopefully not, where the population of humans, say, is 0. So you're never going to have the sort of the p in this case being standing in for the y. You're never going to have the p variable hit the t-axis in this case. And also uh, the fact that at each point in time, the number of people that can reproduce is going to be given by the derivative dp dt, which is obviously the gradient of the graph p with respect, sorry, the graph of p against t. But the gradient is going to be dependent on the height itself. What I mean by that is the number of people that are going to be able to reproduce is going to be dependent on the number of people that are alive at that point in time. So we again get back to this sort of starred equation in the case of population dynamics. And similar things can sort of arise in things like radioactive decay. So perhaps I should sort of say that here by making some sort of space. So application one would be populations, and then another one would be radioactivity, and then there are numerous more applications that it's not really worth sort of getting into. With that, I would like to bring this video to an end. Thank you for watching. We hope you found this useful. If you did, then please do hit the like and subscribe buttons. And as always, do leave a comment in the comment section letting us know what you would like to see more videos on. We will see you in the next video. Thank you for watching.